great pleasure to welcome today Yiwei Lyu, who is joining us from Carnegie Mellon University, where she is a PhD student in ECE with Dr. John Dolan. She is working primarily on robotics, especially at the intersection of control theory, machine learning, and the social sciences. So that's a very interesting area, I think. And her primary research focus there is also on safe robot autonomy, especially within multi-robot systems. She's been recognized a lot for the excellence of her work. In 2024, for example, she was named an Human-Robot Interaction Pioneer, as well as an MIT Rising Star, and her work has been recognized with several Best Paper Awards and finalist nominations. So it's a great pleasure to have you here, and I'm looking forward to listening to your talk on consciousness.
Thank you, Marcus, for the nice introduction. And I'm very happy to be here to share about my research and passion on how can we make robots safer and advance responsible robot autonomy. So robots has become a part of our lives more than ever. We see them on the street, in the hospital, in the warehouse, and even use them for entertainment. And for the robotics industry itself, it is also attracting a lot of investment. With a global market projected to grow from 46 billion to a nearly 170 billion by 2032. This is highlighting both the economic growth as well as the transformative potentials of robotics technologies. And now with robots being increasingly integrated into both our lives and industries, we're really expecting high on responsible robotics, meaning the robots should not only do their jobs efficiently, but should also capable of making decisions that are safe, reliable, and ethically sound. However, before achieving this grand goal, a critical challenge right now is how can we ensure robots stay safe at the very least in physical terms? After all, how can we trust a self-driving car if they're capable of leading us into danger, right? And with the incidents that involving robot workers and autonomous systems on the rise, this has become an increasingly concerning issue. So action has been taken. Agencies like Occupational Safety and Health Administration have issued guidelines on robot safety, emphasizing measurable and quantifiable robot safety standards. However, safety must not come at cost of being overly conservative. So in August 2023, 2 autonomous vehicles blocked an ambulance from leaving the crash site, delaying the transport of the patient and tragically leading to their deaths. So this incident is telling us that the robotic system today, they are not fully equipped to handle these real-world complex situations where safety and flexibility must coexist. And what's even more concerning is that these incidents, although statistically rare, they're already starting to cause public fear on robots, and people will stop using robots if this continues, no matter how innovative or efficient they become. So before we explain why it's so hard for safety and flexibility to coexist, let's first look at some challenges for robots to stay safe in this physical world. So in general, robots observe from the environments and make predictions about how things will unfold in the future. And these predictions will lead to specifications, for example, tell us how far the robot should keep itself away from the object. And then during this decision-making process, the robot will decide what actions to take, either individually or collaboratively with their human or robot teammate. So this process may seem straightforward, but when it comes to real-world applications, it's far more complicated, as robots may face potential sensor failures, unexpected changes in the environment, or unpredictable actions from other agents. So my research aims to address this grand challenge of physical robot safety. And I'll discuss how we can use methods from control theory, machine learning, and social science to investigate it from 3 different perspectives. So we'll be talking about the environments the robot operating, the counterparts they're interacting with, and also the safety specifications they're following. And this brings us to the outline of today's talk. So in this first introductory chapter, we'll talk about functional safety, targeting robots operating in uncertain environments, especially if they're suffering from localization error or motion disturbance. And I'll present a control-theoretic framework that provides mathematical foundations for guaranteeing safety in a probabilistic setting. And more importantly, we want this part to be done without having robots to behaving over-conservative. And second, Building on top of this, together we'll explore the challenge of collaborative safety, where robot has to collaborate with their heterogeneous teammate in a decentralized setting. And I will show how we can use the novel responsibility reasoning combined with control-theoretic methods to allow agents to make context-aware decisions that lead to group intelligence with formal safety assurance. And then in the last chapter of representational safety, we'll talk about how can we generalize these methods to those unseen scenarios where the safety specifications are not known beforehand and have to be learned from them. For example, when a robot enters a new environment, how should it determine what is the best safety distance to follow? And I will discuss how we can blend data-driven learning together with control-theoretic techniques to answer the question of how safe is safe, to allow the robots to adapt and refine their constraints in real time. So to begin with, in this first chapter, we'll talk about three things. What is safe control? Its connection with provable guarantees, and how can we achieve it under uncertainty while allowing robots to stay flexible? So the general idea of safe control is that given a system model that tells us how the robot positions and the velocities are going to change if certain actions are taken, and also given safety specifications that tells us, for example, how far the robot should be away from others, right? And this describes which states are safe for the robot to stay in. Then we use control theory to select actions to keep the system in those safe states. And some common strategies to do that is we can partitioning the joint state space into small tessellations, or we can impose velocity constraint based on geometry and motion, or analyzing all potential future states given robot dynamics. Yeah.
This is the state space of only our robot, or a state space that includes the dynamics of the environment?
This is a state of only robots.
Okay.
Yeah. However, these common strategies usually suffer from limitations, for example, difficulty in handling complex system dynamics, or overly reliance on restrictive assumptions about how others will move, or they could become easily computationally intensive in runtime. So at the same time, control barrier function has become a practical popular solution due to its generality and easiness to use. And here's an overview of how it works. So given a system model like this, where X represents the state of the robot, for example, the position where it is, right? And U is our control input to the robot, for example, the accelerations. Then control barrier function is essentially describing a set of states denoted by this Hx greater than or equal to 0, where H function is characterizing how far the robot is away from the boundary of the same set. So just like in this illustration here, the red safety boundary is separating those safe states with positive H values from unsafe ones. And the control barrier function is essentially saying if the robot starts initially in this set, then it will always be kept, remain within the set. So how can this be done? So we do this by imposing such condition on robot motion to describe what kind of actions are actually allowed or acceptable based on how we would like this H function to change. And here we're strictly enforcing the rate of the change of this H function with respect to time has to be lower bounded by negative gamma H, where gamma is a positive behavior coefficient. Now, how is this related to provable guarantees? Let's look at this visualization here. So we have this blue line here describing how we would like this H function evolves over time. And at the same time, we have this green line. It is an exponential function serving as our baseline function. So the key idea here is as long as we can bound or make sure the decaying rate of this blue line is not faster than this green line, the blue line will always stay above and therefore keeping the positive value for the H functions. Correspondingly, the robot will always stay within this safe set. So we can see CBF is a quite powerful tool as it can translate our safety requirement from the state space into a constraint for in robot action space. So that's why like people use CBF a lot to get these provable guarantees. However, it also has some limitations. The first one is that it often assumes perfect system models, system dynamics. So what would happen if uncertainty, for example, unbounded motion noise is introduced? Can we robustly account for these uncertainties while still preserving these provable guarantees? And second, So think about the cases where the robots blocking the road due to their limited behavior characterization, right? So the question here is, can we make the safety analysis to be adaptive so that we can maximize the robot flexibility in motion while like when it comes to near accident situations, right? So they don't have to become or behave overly conservative. So to address these two challenges, we propose to extend the conventional CBF into a probabilistic setting. Let's take this random merging as an example, where our evil vehicle needs to safely and efficiently merge with this human-driven car here. And instead of having a deterministic model, now we are having a stochastic one with this additional term B capturing the uncertainty model as Gaussian motion noise. And on the upper right, we have this loosely defined probabilistic CBF safety condition. And unlike those traditional CBF that relies on fixed behavior parameter gamma, we are formulating it as a bi-level optimization problem where the robot control as well as the behavior parameter gamma are being involved. Now you may wonder, why do we want to do that, right? How can this help us to address those two challenges we mentioned earlier? So recall the exponential functions we mentioned earlier. The gamma value is essentially describing how fast a robot or system is allowed to approach the boundary of the safe set. So by taking different values of gamma, we are essentially choosing different exponential functions to bound our decaying rate of the H function here. And in the context of driving, this gamma can also be interpreted as driving styles. For example, whether a robot is typically a conservative driver or it is a typically aggressive driver. And our key insight here is when it comes to near accident situations, actions that do not follow your typical driving styles may be needed. So by allowing if a robot becomes normally conservatively, then by allowing robots to become temporarily a little bit more aggressive than it usually is, we're essentially expanding our safe control set to unlock some additional solution space to allow robot to take this flexibility to maneuver, right? And this kind of flexibility greatly enhances the likeness of this safe control region so that robot can complete their task without those unnecessary constraints. And here is our formalized representation of this probabilistic CBF constraint, stating that this condition has to be met with at least probability of sigma. And this kind of formulation allows the robot to robustly account for uncertainties while dynamically adjusting its driving behavior style to balance between safety and flexibility. Now, this probabilistic CBF framework is quite useful as they can provide diverse safe behavior characterization in a systematic way. So let's take this random merging as an example, where evil vehicle here in red needs to merge with other two human-driven cars. And in real-world driving, we would expect very different behavior when we're looking at how an aggressive driver is dealing with this versus a conservative driver, right? And traditionally, if we want to do that, we need to specify very detailed goals. For example, which gap should the robot merge into? And now, after that, once you specify this goal, you will need to construct like corresponding reward functions or use a high-level planner to do that. Now, with our approach, so actually these diverse behavior naturally emerge from the same objective function. And this is because the safe control space for each robot is being automatically calibrated based on the different driving styles they are adopting. And these different behavior aligns well with our real-world applications. I also want to discuss how this adaptive safety analysis can help us in near accident situations. So we're still taking the same random merging as an example. And here in this plot, we are plotting out how the minimum inter-vehicle distance is changing over time. And we are comparing our approach marking green versus the conventional CBF marking brown. Now, this black dashed line here represents the minimum safety margin the robot has to respect. And we are highlighting this green zone where this is when the near accident situation happens. Now, let's see how does our approach handle it. So here, the evil vehicle is set to be a normally conservative driver. And this is where the near accident situation happens. So basically, you have all these different vehicles like interacting in really close proximity when they are approaching to the merging point, right? And what we see that with our approach, the ego vehicle actually accelerates so that it can get in front of others. And this is because with our approach, the ego vehicle can adaptively adjust its driving style. So in this case, it decides to be temporarily a little bit more aggressive than it usually is. And this kind of strategy ensure that it stays safe over the entire past time. However, when it comes to conventional CBF, their behavioral characterization is very limited due to their fixed safety constraint. So that's why they fail to find any feasible solutions and directly implementation. So the key takeaway here is, first, safety does not simply mean slowing down or braking. As we can see from this example, safety means accelerating to get in front of others. So the condition to characterize safe behavior should be adapted based on the specific situations we're talking about. And second, safety and flexibility should and can coexist. Yes.
So this is very interesting, but I wonder how does this work if the other two agents that you're showing here, yellow and blue, are also driven by a similar policy and end up being conflicting in what they consider safe?
Okay, let me rephrase your question. So I guess you're asking, what if we are all having three of those people here,
Yes.
and they are having different understanding of what safety means, right?
Well, I mean, they might all end up behaving according to the policy that you are specifying there, and therefore they might create exactly that scenario that you use as a motivating factor, right? Which is in the individual scenario where you have agents that act independently and one agent that adapts,
Right.
then this works. But if you have three agents that adapt to one another and are therefore, like driven by such a policy, you might end up in exactly a similar situation, right? Where they block one.
Yeah, so in next chapter, we'll talk about when we have multiple agents and how we can deconflict through implicit coordination.
Okay.
Yes, but next question. Yeah, so the second key takeaway here is safety and flexibility should and can coexist. And our probabilistic CBF framework provides us an example of how we can do this. So now what if we're no longer dealing with just one single robot? Instead, we may have a team of robots or a mixture of human and robots, right? Can we still assure safety in such settings? So take driving as an example. Suppose you are the blue driver here trying to do the overtake. The reason that you can do this successfully is because the front vehicle here recognizes your intention to do the overtaking, so it intentionally slows down to make spins, right? So from this example, we can see that achieving collective safety in this multi-agent system is non-trivial. The first reason is that safety can be influenced by a lot of factors, including objective factors, basically where all the agents are and how fast they are moving, and also subjective factors, what kind of agents we're dealing with. And second, for these kind of multi-agent systems, they are decentralized, meaning there's no direct communication about future plans available between agents. So everyone has to plan their own action based on how they predict the other will likely to behave in the future, right? So that's why implicit coordination is usually the key to achieve collective safety in these multi-agent systems. So to address these challenges, we propose our solution to start with a structural safety analysis that provides a unified framework to account for all these different factors in our safety analysis. And then I will talk about how can we use allowable responsibility reasoning to introduce this kind of implicit coordination. So as a part of this structural safety analysis, we'll start from capturing the difference in agent social preferences, where social preferences refers to their different degrees of willingness to cooperate. Existing literature from social psychology tells us that there's a concept called social value orientation, SVO, that can be used to model this kind of internal mental state of others. And it can be represented as an angle, theta, to indicate how an agent weighs its own reward against others. And all these individual points here represent individuals with different social preferences, ranging from egoistic to prosocial and altruistic. Now you may think, okay, this is great. Now can we just grab it and use it in our safety analysis? Unfortunately, no, and here's why. So we're looking at the 4-agent navigation task. Each of them need to get to their goal goal location while appropriately interact with their counterparts or humans. And suppose you're the agent A here, and you consider yourself as a pro-social agent. However, your response to agent B, C, D should also depend on how different their social preferences are from yours. Now, SVO itself simply captures the individual preferences, not the relative differences. So what should we do? To address this limitation, we propose this relative SVO, the RSVO. So basically, instead of treating all individuals as single points, now we're expanding it into a range to capture this behavior pattern of how an agent would adapt its own behavior based on the different social preferences its counterpart now has. Now let's see how this works in a two-agent position swapping task. So in general, if safety is not a concern, then people will just walk in straight lines, right? And now with safety in mind, the question becomes, who should yield and take more detours? So as we expected, when an altruistic agent 1 meets an egoistic agent 2, the altruistic agent 1 starts to deviate from its nominal trajectory at an early stage and take a much longer detour before reaching to its destination. However, this doesn't mean it will always behave the same way when it is interacting with a counterpart with different social preferences. So actually, in this example, from left to right, we see that when the same altruistic agent 1 is interacting with a counterpart who is also become increasingly altruistic, the agent 1 itself is also delaying the deviation and shorten the detour, right? So from this example, we can see RSVO can effectively capture these different behavior patterns by explicitly analyzing the relative social differences between the pairwise agents. Now you may think, okay, this is great, but how can we get this RSVO value, right? So in another work, we show that RSVO value can actually be learned from time sequential data, for example, trajectories. And the data we use, including the distance to others, as well as the gradient of this H function that depending on states and motion. And then we show that by using supervised learning, we can actually infer the likelihood of this RSVO value, as well as the associated safe control classes that the others might be implicitly following. So here, instead of using traditional machine learning techniques that directly predict where the other agents might go, we are more interested in where the other agents might not go to capture this behavior pattern. And since this behavior pattern is not directly tied to any task-specific setting, this allows the robot to have capture an easier and more effective interactions in complex situations. So now we have talked about how to handle interactions between two agents, but how does that work if we want to generalize it to multiple agents? Actually, with increasing numbers of agents in the system, the challenge now shifts towards how can we assure collective safety that requires behavior not only safe for individuals, but also promotes safety for the entire system. And just one of the intuitive examples is like while driving, we would expect the driver to not only take those necessary actions to keep itself safe, but also it should proactively navigate to those spaces that are less crowded, right? And how can we reflect these considerations in a unified framework? So that's why we propose this holistic risk metric visualized on the left that incorporate all these different factors, including where all the agents are, how fast they are moving, and how different they are from each other, which is measured by this RSVO value. And on top of this, we're using conditional value at risk, CVAR, to quantify the uncertainties associated with each factors. And then by surrogating it from surrounding agents, the metric risk I is essentially telling us how much risk the agent I is receiving from the environment. And more importantly, how likely the safety violation may happen even if it is safe for now. So now this risk assessment basically gives us a way to understand what kind of environment we are in. Now the next question becomes, how can we leverage this information and guide the robot control, right? So think about the two robots navigating in this shared environment. And if one robot, and each of them has to plan their own safe behavior based on how they think the other is likely to move. And if one robot thinks that its counterpart is only going to spend the minimum effort to avoid collisions, then itself must adjust its action to take on more responsibilities to maintain safety, right? So this naturally leads us to the concept of responsibility allocation. And our key idea here is, in order to achieve collective safety, we can actually distribute the responsibility shares among individual agents to quantify how much effort an agent should contribute towards such collective goal. And on the right, we are showing how this can be formalized through the collective CBF constraint, which essentially describing in this multi-agent system, for each individual agent, your safe control space should be characterized based on the amount of responsibility shares you got assigned and the contribution of all individual agents sum up to guarantee this system-wide safety. Now let's see how this responsibility works in a specific example. So here the red agent is trying to figure out how much responsibility the green agent can realistically take in this setting. And it does this through counterfactual reasoning. Specifically, it imagined a counterfactual scenario where there is only the green agent and itself in the scene. And by comparing the risk evaluation from this actual environment and the counterfactual environment, the red agent is essentially explicitly reasoning about how the existence of the blue agent is influencing the interaction dynamics between the green agent and myself, right? And now in this specific example, we see that the existence of the blue agent poses a much higher risk on the blue agent, expanding its risk level set, indicating that the green is suffering a much tighter motion constraints. So that's how the red agent decided to take on more responsibilities on its own. Now the question becomes, okay, we have these responsibility shares. Now how are we going to inform robot control, right? And then we does this through embedding the responsibility shares into the process where we characterize the certifiable action space for individual agents. And we prove that through this kind of decentralization, we can actually provide a sufficient condition to satisfy the system-wide safety. Now, the advantage of doing this is that each agent, they can independently compute about their safe control without predicting what the others are going to do in the future, while at the same time maintain implicit coordination with others, where implicit coordination comes from this responsibility reason. Now let's see how this responsibility allocation works for multi-vehicle collaborative testing, driving. So basically we have 3 autonomous vehicles and they are all going to use the same, our policy, basically they're going to characterize their safe control space based on how much responsibility they got assigned. And on the right, we're showing how this responsibility allocation can dynamically change over time. And let's see if that makes sense. So we have 3 subplots here, and the first and third subplots, they are quite intuitive to understand, because what happens was, as the red vehicle nudges into the gap, the risk it receives becomes significantly higher over time. So that's why its counterpart to decide to take on more responsibilities on themselves. So what's particularly interesting here is the second plot, where we see there are actually 2 swaps between the yellow vehicle and the blue vehicle. Now let's zoom in to see what happens. So the first swap happens when the red vehicle just nudges into the gap. So before it does that, the yellow vehicle only has one following car, which is the blue one, right? And now with red merging to the lane, the risk the yellow vehicle receives becomes significantly higher, and that's why it leads to the drop of its responsibility share here. And now as time goes, the yellow vehicle also starts to feel this increased pressure on itself. So it decides to accelerate to keep a longer distance from a longer safety distance from the following vehicles. And this action proactively reduces the risk it receives from the environment and therefore leading to the rise of its responsibility again. So from this example, we can see how each agent are reason about their own responsibilities based on their risk evaluation from the environment, which aligns well with our design intuition. So here we want to show our approach, how does it compare to non-risk aware baselines. So basically here we're using the same decentralized mobile robot team, but no responsibility reasoning. And since they only care about like their own objective functions, they quickly fall into a deadlock and take a longer time to resolve. However, on the right, for example, pay attention to this robot, right? So our responsibility reasoning allows it to think about what kind of role it should take in such collaborative setting. So here it realized, oh, I'm in a much tighter constraint space, receiving much higher risk from the environment. So it's a better idea for me to stop where I am and make rooms for others to pass first. And this kind of implicit coordination allows the robot to complete the tasks more efficiently. And it is also from the same example, we draw the conclusion that egocentric behavior doesn't always lead to better decisions. Additionally, the implicit coordination from our work also proves valuable in resolving general deadlock situations. We also extend our approach to a mobile robot team with 16 robots. So they are doing safe navigation tasks, trying to avoid collision here, and all these colorful regions you see here are visualizations about how each agent reasons about their own safe zone. And by ensuring that these colorful regions are non-empty and non-overlapping, we can provide like formal guarantees for this system-wide safety. So the key takeaway here is, first, behavior that is safe for individuals may not be the behavior that is best for the entire team, as we have to be cautious about this potential cascading effects. And second, in this kind of decentralized multi-agent system, implicit coordination is the key to achieve collective safety. And our responsibility reasoning provides us an example of how we can use control theory to bridge the insights we draw from social science to formalize these kind of implicit coordination. Okay, so far we have talked about how should the agent either act or how should an agent act either individually or collaboratively as a part of group when there's clear definition of what safety means, right? So what would happen if we don't have these safety specifications known beforehand?
So let me interrupt you for a second. Let's go back and look at robot 15, because this was really fascinating behavior. And so it's going to have reached its target, be static, have reached its goal. It is being approached by a robot that has a safe path, and yet it's still going to move out of the way. And so is that right?
Let me play this video.
So upper right, yeah.
Which one are we talking about?
15 reaches its target,
15. Where's it?
upper right.
Here,
And
right?
it's going to move out of the way in response to 6, who has a
Right.
safe path.
Mhm.
And I'm just surprised that that's feasible in this optimization framework.
Right. So I think what happens here is they are essentially trying to reason basically their safety constraints, right? And we are allowing robots to temporarily deviate from their goal position, even if they have reached to their goal, to maximize the overall efficiency. So if you want the robot to stay where they are, once they reach to the goal, we can do that by adjusting basically you can specify, keep at where you are once you reach to the goal. Yeah, and the reason we can see this, as we mentioned earlier, like we are essentially trying to incorporate these kind of implicit coordination in their safety constraints, right? And this allows them to reason whether I should make more rooms for you to pass first, or whether I should stay where I am and I should have the right of the road. That's the intuition behind it. Any more questions?
I think it opens an interesting question, right? Because when you look at it closely, actually 2 does the exact same thing, right? Where I would argue that being altruistic is great, but then at some point, I think at some point, right, it becomes a lot of. It seems to be that that the framework involves a lot of prior encoding of what desirable behavior is.
Right.
Right.
Yes, that's a good point. So underlying here, the point is, the reason we can get this implicit coordination is that we are encoding what kind of information we should take into account when we're doing this responsibility allocation, right? Responsibility reason. And potentially that is including the RSVO value, how different the agents are from each other, or whether this robot is a more aggressive agent compared to others. And in practice, I think it will open interesting discussions on if we don't have this prior information available, and we'll have to learn it from interactions.
So here the agents know what the behavior of other agents is. So you're not learning, for example, 15 and 2 don't recognize that 6 is, I don't know, like a drunkard who's coming up there and is gonna, like, interact. This is not learned.
Right, in this part, this is not learned. But in the previous one where we show RSVO can actually be learned, those are a separate work from like how we can learn RSVO value from how the agents behave with their trajectories. Okay. I will continue.
I guess one
Yeah.
last related question to that is, you have that, I have other questions on the learning of it, but I'll maybe hold those to the end. Does it make sense in a system like this to treat that as some other optimization parameter? Like you have some general objective you're trying to accomplish, like find the right amount of altruism for everyone to make sure that you minimize the overall sort of movement, that sort of thing? Or is this is presuming someone's given you, like, this is an incredible, this is a really nice robot, now solve the problem?
Good, very good question. So the motivation of this work is saying that we have this robot team, but there's no centralized method that we can send a direct command to each robot saying what you should do and what he should do.
Mhm.
So instead, we're trying to come up with a decentralized decision-making process so that each robot can reason about what itself needs to do without predicting what others need to do. And responding to your question about whether we can formalize this through a unified optimization problem, yes, we can do that, but that will be in a centralized optimization, right? You have to compute it from a basically God view, global perspective, to say who should do what. And here we're saying how we can translate this centralized decision-making into decentralized manner so that each agent can come up with their own safe control while being implicit coordinating to others.
Yeah, I guess I was talking about it seems like there's a hyperparameter here, right? Which is like how nice versus aggressive each robot is.
Mhm.
And your point would be, like, in principle, you could try a bunch of different settings of those across the robots and then see how the decentralized planning goes. But you'd need some way to predict sort of how the decentralized system will evolve, and that requires a centralized view. And so you sort of can't, that sort of defeats the purpose of doing this in a, I don't know if that makes sense. I guess my question was, like, it feels like this is a hyperparameter. Could you tune the hyperparameter? I'm a machine learning person, so
Are we talking about the aggressiveness of the
aggressiveness of the individual units. Like, it's not obvious to me why the robot should have different sort of priorities, if that makes sense.
Right, so this is basically what happens when in real world application, let's say you have a bunch of Amazon mobile robots and they're trying to do the deliveries or sorting the priorities to send the deliveries, right? Some might be carrying those overnight shipping and others might be carrying 2 days shipping that, right? And those are essentially like one way to represent different priorities or different aggressiveness level.
Got it. That
Yeah.
makes perfect sense.
All right, so in this first chapter, we'll talk about if we don't have those safety specifications clearly defined beforehand, how can we learn it from data, right? And in this chapter, we'll mainly talk about what is the constraints in learning-enabled systems, the connections between constraints and specifications, as well as how can we learn those underdefined specifications from data. So in general, learning-enabled systems, we want to come up with a policy to inform robot control, usually under the guidance of constraints. And these constraints might be the safety distance or the region of operation that people have widely used in the safe area framework for autonomous racing and robot-assisted surgery. However, the assumptions that these constraints are often known beforehand is problematic. Actually, as robots operating in these dynamic and unpredictable environments, the constraints are actually either unavailable or insufficient to adapt. So what does that mean? First, it may indicate that we are facing unknown parameters of the constraints. For example, when a robot enters a new environment, right, how should it determine what is the best safety distance for it to follow? And second, it may indicate that we are facing unknown structures of specifications. So when a task can be achieved through different combinations of constraints, how should a system determine which set of constraints to follow? So to answer these questions, we propose a principled way to learn both specific constraints as well as their compositions. So what we do is we use machine learning model to learn those data-driven constraints that best capture the underlying complexity and dynamic nature of the environment. And then through combinatorial optimization, we figure out what is the best way to select and compose different constraints together to meet level specifications. And what makes our approach unique here is the co-design process with calculus. So instead of treating robot control and specifications as two independent components, we're actually optimizing the robot behavior while refining our understanding of the constraints. And this kind of co-design allows the system to better adapt to evolving tasks and environments. Now let's see how this works with an example of mobile robot team with communication constraints. So the task is pretty simple, right? Spread out to complete a task while staying connected. However, this only tells us what needs to be done instead of how we can do this. And this underdefined specification essentially requires us to answer two questions. First, how should a robot determine what is the optimal distance for it to maintain reliable communication quality, especially considering when signal strength could vary across space as robot moves? And second, in this mobile robot team, how should we determine which neighbors we should connect to preserve this global connectivity, which means like each robot has to at least indirectly connect to each other in the team. So to answer these questions, we start from collecting some real-world data. So this is how we resemble a typical indoor space. And by using materials like foils and wooden boards, we are simulating the existence of interior metal walls and wood walls, which are common factors that can influence communication quality. On the right, we are looking at a visualization of how this communication quality could vary over space. This is measured by a metric called RSSI, receive signal strength indicator, to quantify the signal strength of the Wi-Fi signal strength at different locations. Now, with this data, including robot positions as well as the measured signal strength, let's see how we can learn the constraints as well as their compositions from this data. So we start from building a predictive model using Gaussian process to estimate the communication quality around each robot. And then from this predictive model, we define a region with acceptable communication range, basically representing within this area, we can receive acceptable communication quality. And then we formalize this region description through connectivity barrier certificate, which basically translates the communication requirement from the state space into robot control space. In other words, for this pairwise robot INJ, as long as we can find a joint control that falls within this part of this set, then this pairwise robot is guaranteed to stay connected. Now, with connectivity barrier certificate serving as our pairwise and modularized constraint, our next question here is, in this mobile robot system, how should we determine which subset of the constraints to activate, right? And at the same time, we want to minimize the unnecessary constraints on robot motion so that they can complete their tasks efficiently. So we do this through graph-theoretic optimization, which can help us compose all these different pairwise constraints into a unified framework. And through this process, we can ensure that the robot team stay connected as a whole while maximizing their flexibility in motion to reach to their target. And then the robot take actions from this unified set of constraints that incorporate both safety and communication requirements. And now as robot go to new locations, the new data they continue collected will be further used to refine the understanding of the constraints. So that's why with our approach, the robot behavior as well as the constraint understanding are being collectively improved over time. So before we show our approach, I want to show a baseline version. So basically, we have 6 differential drive compiler robots divided into 2 subteams, and they need to reach to their goal locations separately. And now with this baseline version, we are not enforcing any constraints. So we observe that collision happens, and also the robot team lose connectivity. Now with our approach, we can see that the robots can actually reach to their goal locations effectively while staying connected and safe over the entire time. And on the right, you're looking at a visualization of how the communication constraints are being established within this multi-robot team. All these different dots are representing the agents where the robots are, and the links here representing the communication constraint is being established between a pairwise robot. Now you will see two changes. The first change is in the length of the link over time. And this is because for pairwise robots, they're actually adapting their communication constraints based on the received signal strengths they are receiving at those particular locations. And second, you will see a change in the way these links are being connected. And that's because during this process, we're dynamically choosing or composing different pairwise constraints together to meet this high-level specification saying this robot team has to stay connected. So the key takeaway here is when we are talking about evolving tasks and environments, the co-design between robot control and specification is really important. And second, when we are facing underdefined specifications, this might be effectively addressed if we can integrate data-driven learning together with control-theoretic techniques. Okay, so as a summary, today we have talked about how should a robot act either individually or as a part of group under uncertainty, and how can we generalize this method to unseen scenarios where safety specifications are not known beforehand and have to be learned from data. Now, where are we going next? The one important question that is driving my research is that considering robots transitioning from being tools to digital citizens in our human society, we should not only how can we better reflect the definition of robot safety, right? And to me, it means that we should not only pay attention to robot safety in this physical space, but also pay attention to the long-term societal impact. So what does that mean? The first direction I would like to propose is called human perceived safety, with a focus on trustworthy behavior synthesis. So imagine you're driving on the road, and if you see a self-driving car crazily weaving through traffic like this, although it's technically safe, I mean, there's no collision happen, but you don't want to be anywhere close to it. So the question here is how can we capture these considerations and incorporate it into robot decision-making so that we can better align robot behavior with human values and perceptions? This is the challenge I want to tackle. And then the second question is about ethical robot safety. So the key idea is that I want to give the robots ability to critical thinking about what is right. So rightness might be described by a lot of things. It could be moral standards, it could be social norms, right? And this will be especially important when robots trying to navigate in complex situations where there might be conflicting values. For example, as a car driving on the road, you should follow traffic rules. But if you're an ambulance car on active duty, you should know when to break the rules to save lives. So the key challenge here is how can we enable context-aware ethical reasonings to determine which set of norms should be applied based on the context we are talking about, and how can we balance between conflicting values during execution. And then the third direction is about legal robot safety. So this is a new area that is currently quite under explored, and the key idea here is I want to extend the responsibility reasoning in my current research that answer the question what the robot should do to avoid collision to liability reasoning in the legal context to answer the question, given the accident has already happened, is there anything that you could have done better? So ideally with this kind of framework in the future, if a self-driving car is again involved in a multi-car crash, then our framework should be able to tell whether or not the autonomous vehicles should be held accountable or not. And if so, to what extent, right? So the key challenge here is how can we codify or translate those high-level abstracted legal terms into computational constraints that can be incorporated into robot decision-making for direct execution so that we can make this entire decision-making process to be not only computationally trackable, but also legally trackable. And with these all three directions, I hope to advance responsible robot autonomy so that we can foster trustworthy, ethically sound, and legally compliant robot decisions and behavior. And finally, here's my robotics research roadmap. And these are the work that have been highlighted in today's talk. And I'll be happy to chat more offline. And lastly, I want to conclude my presentation with a big thank you to my dear mentors and collaborators for their help and support. Thank you.
We have some time for questions.
I'll start. I didn't ask any during the talk, but great presentation. And so you're you're focusing on the safety of robots that basically are functioning correctly and are just trying to interpret their environment.
Mhm.
But you're also thinking about, faults or failures within the robotic and how you might incorporate that. Because especially, I think that example you had with the ambulance being blocked by the cars, those cars were fail safe. Basically, there was whatever reason they failed, they stopped. Normally that's considered fail safe, but in this scenario, it's not really safe, right? You need more
Right.
fault tolerance.
Exactly. So I think that requires us to have a better understanding of what safety means.
Mhm.
So that's why I think safety reasoning should be context-based. Like
Yeah.
you have to determine what safety means in different situations. For example, safety in terms of like simple collision avoidance, as we shown in
Yeah.
earlier examples, is definitely different ideas when we talk about safety for surgical robots,
Mhm.
right?
Yeah.
Safety in those contexts might be whether the robot behavior is occluding the human operator's view of sight. It might also be how well the robot behavior is aligning well with surgical intuitions. So I think the key idea here is whether we can have a better understanding of what safety means based on the context we are talking about. And if we're able to do that, then we can formalize like better, like those kind of fail-safe behavior or robust safe behavior. In different
Because even in the examples you did with all the sort of vehicles moving around, let's say one camera failed on one of the vehicles, what should it do in that scenario? Like, do you have a way of incorporating that in your formulation?
Yeah, good question. So in the current formulation, then what we can do is basically that's saying we have our way of modeling the uncertainty changes, right?
Mhm.
You have larger uncertainties.
Yeah.
And then we can do this by robustly account for it with those probabilistic CVF framework. So that is basically a framework that can account for uncertainties you have in the system and try to design a robot control or behavior that can compensate these kind of quantifiable uncertainty.
More questions?
More. I guess the it's sort of a broad question about sort of exploration versus exploitation in some of these problems.
Yeah.
Like in the, towards the end, you talked about the example where the Wi-Fi signals might not be as good in different parts of the room.
Mhm.
I guess I had a particular question around that, which was like, to what extent are the robots actually optimizing to learn about that versus just incidentally they learn about it as they move around? But they're sort of operating on the knowledge they have originally with the data you gathered. They solve the problem as best they can. As they do that, they're going to move around, so they'll get more information, but didn't seem like they were like optimizing to learn more about that. I guess that would be a specific question about that project, but I guess more generally, in regards to the answer, what the answer to that is, I'm sort of curious how you are thinking about, if you're thinking about sort of going in that direction of figuring out sort of what amount of exploration is required, and maybe like in what situations, like, do you just need data to bootstrap on in the first place? Because I could imagine in some of the relative preference work, if I don't know the preferences of someone else, I might not want to test them to find out what their preferences are by, say, doing something aggressive and seeing how they respond, even if that might be useful information for understanding their preferences. So I'm sort of curious how you think about that.
Yeah.
Broadly.
Very good question. So in the current work setting, for example, the communication example we show here, we are not actively learning, or we are not actively planning the robot behavior in a sense to learning what the communication should look like in those particular locations. Instead, so we are saying, as robot goes to new places, it collects some communication data in those particular locations and how it is using those knowledge to refine its understanding.
Mhm.
But I think the question you raised is very interesting because this is also one of the problem we encounter with human model. Like I can give a very intuitive example. Let's say we're at an intersection and there's no traffic light, no stop sign. And now we have an autonomous vehicle approaching to the same intersection almost at the same time as a human did on top. And usually what people do is we will have a human model that is learned from how the human behave in past 3 seconds, right? These kind of passive observations. And our key insight is that it's not really helpful to help us understand whether that human is altruistic enough to yield to us, just simply based on how it drives itself in like last 3 seconds. Instead, in real world, like in our daily lives, what we usually do is we will nudge a little bit forward to see how the other vehicle reacts, right? And this kind of probing behavior can actually bring us some observations of some hidden information about the human model we're interested in. So that's why I didn't include it in my talk, but in one line of our work is how can we co-design the robot learning and control so that we can strategically plan the robot behavior to cultivate or encourage some probing behavior so that we can better understand what kind of human model we are dealing with. So basically safe exploration and exploitation at the same time.
Oh, that's
Yeah.
great. It's a nice anecdotal example.
Thank you.
Thank you for the great talk. I have 2 questions. The first one is I'm thinking about all these like robot behavior. I'm wondering like, is there like a response time that you're programming into these robots? And I feel like the response time of humans versus robots can be very different. So I'm thinking like, is there like a way to like optimize this response time?
So for this response time, are we talking about computational time or like how fast the optimization problem can be solved? Is it the question you're?
It's more like once you like detect or predict that something's going to happen, like there's the detection part and then you actually responding to like what you're gonna like do, like according to what you detect. And I feel that a lot of accidents happen because even if you detect it at the point like where you're responding, you can't respond fast enough.
I see what you're saying. Okay, so let me explain this a little bit. So from the way these approaches are being designed, we are focusing a lot on real-time execution or computation. So basically, these optimization can be solved in runtime, ensuring the robot can react like in time when they are responding. However, I think the question you want to ask might be related to whether it is not too late for you to react, right? And the criteria of whether you are too late to respond is based on the feasibility actually about these problems. For example, if we are talking about self-driving cars, maybe like you're already too close to others. This is not because you perceive this too late, it's because you're already in that physical state. And no matter what kind of decisions you choose, then there's no feasibility anymore, meaning no matter what you do, you will have to collide. Then in this case, our approach, like since there's no real solution exists in this real world, so our approach cannot handle that as well. However, our approach, what it can guarantee is if there actually exists a feasible solution in the physical world, then our approach can guarantee to find it.
Well, but I think another, like, my interpretation of your question is different. And I think that I don't know, I think I find my interpretation more interesting. And that is because it's for something else, because I think that this is the feasibility. I mean, this is the obvious answer, right? Like if you can't do it, well, then you can't do it. Okay, well, great. But I think that if you're thinking about the social aspects, the question has different meaning, because if you design for real-time applicability, humans are not real-time, right? Like humans are not that straightforward in the sense that whenever they perceive something, they will be like snap on to respond in the way that you are thinking that they will, right? They might take time in processing. They might not be paying attention to that specific cue, right? So if you're thinking about the question that Michael was asking earlier, and you were answering about this co-design of planning and probing, right? Like all of that makes sense, but it makes very strong assumptions about people, how people are reacting. And this is, I think, where Jasmine's question is going as well, right? Where like, if you have a system that behaves in a certain way, you need to think about the delay with which you expect to see reactions from the world potentially, right? So, because again, right, like, of course, if you are the sole actor and you can avoid something by breaking, it either is too late or it's not too late, and you can implement it. But I think it is more about cooperatively finding an equilibrium state that works for everybody. I think delay plays a huge role, right? Because you have to make assumptions about how other players are going to interpret and react.
That's true. That's true. Yeah, I think one step forward would be, for example, when we are considering a more realistic, for example, human modeling. Right now, we are currently still assuming human like decisions will be in real time, right? Or response will be in real time. then I think that requires us to have a better understanding of the human model we're dealing with. For example, there might be some uncertainty in its response time, so that we can quantify this kind of uncertainty and incorporate into robot decision making, so that we can also be able to detect the potential time delay and also correctly identify what might be the potential response the human could generate.
Great. We're on time. You had one more question?
Yeah, I just had a connecting question to this, and I think this is relevant to the definition of safety that you mentioned. And I think throughout the talk, you define safety as not colliding. And so in accordance to when accidents are bound to happen because you don't respond in time or whatever, have you thought about how to define safety in terms of how to minimize the damage, if damage is going to occur?
Yeah. And that's a very good question. So although we didn't explicitly account for that in my current work, however, our approach does provide a very systematic way to assess how likely the safety violation may happen. And if it has to happen, then how serious the violation could be. So this is essentially saying that we have ability to assess the potential consequence associated with each candidate actions. And I think this will be very important with the example let's say, if we have a home care robot, it wants to assist an elderly, right? So on one hand, you want to ensure the elderly doesn't fall to cause harm. However, on the other side, you also want to respect the human's autonomy. So this can be so our approach can be used to assess these potential outcomes or consequences in terms of safety violations. And this could be helpful to, I think, addressing the question you raised. Yeah.
Thank you.
Okay, this puts us in time, and I think you're going to lunch, so you will have time to chat about this a little bit longer. Let's thank our speaker one more time.
Yes.
You're not gonna be able to say that.
I told Russ again. Then will be their job.
Yeah.